A pendulum is a weight suspended from a pivot so that it can swing freely. When a pendulum is displaced sideways from its resting equilibrium position, it is subject to a restoring force due to gravity that will accelerate it back toward the equilibrium position. When released, the restoring force combined with the pendulum's mass causes it to oscillate about the equilibrium position, swinging back and forth. The time for one complete cycle, a left swing and a right swing, is called the period. The period depends on the length of the pendulum, and also to a slight degree on the amplitude, the width of the pendulum's swing. From its examination in around 1602 by Galileo Galilei, the regular motion of pendulums was used for timekeeping, and was the world's most accurate timekeeping technology until the 1930s. Pendulums are used to regulate pendulum clocks, and are used in scientific instruments such as accelerometers and seismometers. Historically they were used as gravimeters to measure the acceleration of gravity in geophysical surveys, and even as a standard of length. The word pendulum is New Latin, from the Latin pendulus, meaning hanging. The simple gravity pendulum is an idealized mathematical model of a pendulum. This is a weight on the end of a massless cord suspended from a pivot, without friction. When given an initial push, it will swing back and forth at a constant amplitude. Real pendulums are subject to friction and air drag, so the amplitude of their swings declines. Period of oscillation. The period of swing of a simple gravity pendulum depends on its length, the local strength of gravity, and to a small extent on the maximum angle that the pendulum swings away from vertical, θ0, called the amplitude. It is independent of the mass of the bob. If the amplitude is limited to small swings, the period t of a simple pendulum, the time taken for a complete cycle, is where L is the length of the pendulum and g is the local acceleration of gravity. For small swings, the period of swing is approximately the same for different size swings. That is, the period is independent of amplitude. This property, called isochronism, is the reason pendulums are so useful for timekeeping. Successive swings of the pendulum, even if changing in amplitude, take the same amount of time. For larger amplitudes, the period increases gradually with amplitude so it is longer than given by equation. For example, at an amplitude of θ0 equals 23 degrees it is 1% larger than given by. The period increases asymptotically as θ0 approaches 180 degrees, because the value θ0 equals 180 degrees is an unstable equilibrium point for the pendulum. The true period of an ideal simple gravity pendulum can be written in several different forms, one example being the infinite series. The difference between this true period and the period for small swings above is called the circular error. In the case of a typical grandfather clock whose pendulum has a swing of 6 degrees and thus an amplitude of 3 degrees, the difference between the true period and the small angle approximation amounts to about 15 seconds per day. For small swings, the pendulum approximates a harmonic oscillator, and its motion as a function of time, t, is approximately simple harmonic motion, whereas a constant value, dependent on initial conditions. For real pendulums, corrections to the period may be needed to take into account the buoyancy and viscous resistance of the air, the mass of the string or rod, the size and shape of the bob and how it is attached to the string, flexibility and stretching of the string, and motion of the support. Compound pendulum. The length L of the ideal simple pendulum discussed above is the distance from the pivot point to the center of mass of the bob. Any swinging rigid body free to rotate about a fixed horizontal axis is called a compound pendulum or physical pendulum. The appropriate equivalent length L for calculating the period of any such pendulum is the distance from the pivot to the center of oscillation. This point is located under the center of mass at a distance from the pivot traditionally called the radius of oscillation, which depends on the mass distribution of the pendulum. If most of the mass is concentrated in a relatively small bob compared to the pendulum length, the center of oscillation is close to the center of mass. The radius of oscillation or equivalent length L of any physical pendulum can be shown to be where I is the moment of inertia of the pendulum about the pivot point. M is the mass of the pendulum, and R is the distance between the pivot point and the center of mass. Substituting this expression in above, the period T of a compound pendulum is given by, for sufficiently small oscillations, a rigid uniform rod of length L pivoted about either end has moment of inertia I equals mL2. The center of mass is located at the center of the rod, so R equals L2. Substituting these values into the above equation gives T equals 2 pi square root 2 L, 3 grams. This shows that a rigid rod pendulum has the same period as a simple pendulum of 2/3 its length. Christian Huygens proved in 1673 that the pivot point and the center of oscillation are interchangeable. This means if any pendulum is turned upside down and swung from a pivot located at its previous center of oscillation, it will have the same period as before, and the new center of oscillation will be at the old pivot point. In 1817, Henry Cater used this idea to produce a type of reversible pendulum, now known as a Cater pendulum, for improved measurements of the acceleration due to gravity. History. One of the earliest known uses of a pendulum was a first-century seismometer device of Han Dynasty Chinese scientist Zhang Heng. Its function was to sway and activate one of a series of levers after being disturbed by the tremor of an earthquake far away. Released by a lever, a small ball would fall out of the urn-shaped device into one of 8 metal toads' mouths below, at the 8 points of the compass, signifying the direction the earthquake was located. Many sources claim that the 10th century Egyptian astronomer Ibn Yunus used a pendulum for time measurement. But this was an error that originated in 1684 with the British historian Edward Bernard. During the Renaissance, large pendulums were used as sources of power for manual reciprocating machines such as saws, bellows, and pumps. Leonardo da Vinci made many drawings of the motion of pendulums, though without realizing its value for timekeeping. 1602. Galileo's research. Italian scientist Galileo Galilei was the first to study the properties of pendulums, beginning around 1602. The earliest extant report of his research is contained in a letter to Guido Ubaldo dal Monte, from Padua, dated November 29, 1602. His biographer and student, Vincenzo Viviani, claimed his interest had been sparked around 1582 by the swinging motion of a chandelier in the Pisa Cathedral. Galileo discovered the crucial property that makes pendulums useful as timekeepers, called isochronism. The period of the pendulum is approximately independent of the amplitude or width of the swing. He also found that the period is independent of the mass of the bob, and proportional to the square root of the length of the pendulum. He first employed free-swinging pendulums in simple timing applications. His physician friend, Santorio Santorii, invented a device which measured a patient's pulse by the length of a pendulum, the pulsologium. In 1641, Galileo conceived and dictated to his son Vincenzo a design for a pendulum clock. Vincenzo began construction, but had not completed it when he died in 1649. The pendulum was the first harmonic oscillator used by man. 1656. The pendulum clock. In 1656, the Dutch scientist Christian Huygens built the first pendulum clock. This was a great improvement over existing mechanical clocks. The best accuracy was increased from around 15 minutes deviation a day to around 15 seconds a day. Pendulums spread over Europe as existing clocks were retrofitted with them. The English scientist Robert Hooke studied the conical pendulum around 1666, consisting of a pendulum that is free to swing in 2 dimensions, with the bob rotating in a circle or ellipse. He used the motions of this device as a model to analyze the orbital motions of the planets. Hooke suggested to Isaac Newton in 1679 that the components of orbital motion consisted of inertial motion along a tangent direction plus an attractive motion in the radial direction. This played a part in Newton's formulation of the law of universal gravitation. Robert Hooke was also responsible for suggesting as early as 1666 that the pendulum could be used to measure the force of gravity. During his expedition to Cayenne, French Guiana in 1671, Jean Ritchie found that a pendulum clock was 2.5 minutes per day slower at Cayenne than at Paris. From this he deduced that the force of gravity was lower at Cayenne. In 1687, Isaac Newton in Principia Mathematica showed that this was because the Earth was not a true sphere but slightly oblate from the effective centrifugal force due to its rotation, causing gravity to increase with latitude. Portable pendulums began to be taken on voyages to distant lands as precision gravimeters to measure the acceleration of gravity at different points on Earth, eventually resulting in accurate models of the shape of the Earth. 1673. Marin Mersenne and René Descartes had discovered around 1636 that the pendulum was not quite isochronous. Its period increased somewhat with its amplitude. Huygens analyzed this problem by determining what curve an object must follow to descend by gravity to the same point in the same time interval, regardless of starting point, the so-called autochrone curve. By a complicated method that was an early use of calculus, he showed this curve was a cycloid, rather than the circular arc of a pendulum, confirming that the pendulum was not isochronous, and Galileo's observation of isochronism was accurate only for small swings. Huygens also solved the problem of how to calculate the period of an arbitrarily shaped pendulum, discovering the center of oscillation, and its interchangeability with the pivot point. The existing clock movement, the verge escapement, made pendulums swing in very wide arcs of about 100 degrees. Huygens showed this was a source of inaccuracy, causing the period to vary with amplitude changes caused by small unavoidable variations in the clock's drive force. To make its period isochronous, Huygens mounted cycloidal-shaped metal chops next to the pivots in his clocks. That constrained the suspension cord and forced the pendulum to follow a cycloid arc. This solution didn't prove as practical as simply limiting the pendulum's swing to small angles of a few degrees. The realization that only small swings were isochronous motivated the development of the anchor escapement around 1670, which reduced the pendulum swinging clocks to 4 degrees to 6 degrees. 1721. Temperature-compensated pendulums during the 18th and 19th century. The pendulum clock's role as the most accurate timekeeper motivated much practical research into improving pendulums. It was found that a major source of error was that the pendulum rod expanded and contracted with changes in ambient temperature, changing the period of swing. This was solved with the invention of temperature-compensated pendulums, the mercury pendulum in 1721 and the gridiron pendulum in 1726, reducing errors in precision pendulum clocks to a few seconds per week. The accuracy of gravity measurements made with pendulums was limited by the difficulty of finding the location of their center of oscillation. Huygens had discovered in 1673 that a pendulum has the same period when hung from its center of oscillation as when hung from its pivot, and the distance between the 2 points was equal to the length of a simple gravity pendulum of the same period. In 1818, British Captain Henry Cater invented the reversible Cater's pendulum, which used this principle, making possible very accurate measurements of gravity. For the next century, the reversible pendulum was the standard method of measuring absolute gravitational acceleration. 1851. Foucault Pendulum. In 1851, Jean-Bernard L'Acuto and Foucault showed that the plane of oscillation of a pendulum, like a gyroscope, tends to stay constant regardless of the motion of the pivot, and that this could be used to demonstrate the rotation of the Earth. He suspended a pendulum free to swing in 2 dimensions from the dome of the Pantheon in Paris. The length of the cord was 67 meters. Once the pendulum was set in motion, the plane of swing was observed to precess or rotate 360 degrees clockwise in about 32 hours. This was the first demonstration of the Earth's rotation that didn't depend on celestial observations, and a pendulum mania broke out, as Foucault pendulums were displayed in many cities and attracted large crowds. 1930. Decline in use. Around 1900, low thermal expansion materials began to be used for pendulum rods in the highest precision clocks and other instruments. First invar, a nickel-steel alloy, and later fused quartz, which made temperature compensation trivial. Precision pendulums were housed in low-pressure tanks, which kept the air pressure constant to prevent changes in the period due to changes in buoyancy of the pendulum due to changing atmospheric pressure. The accuracy of the best pendulum clocks topped out at around a second per year. The timekeeping accuracy of the pendulum was exceeded by the quartz crystal oscillator, invented in 1921, and quartz clocks, invented in 1927, replaced pendulum clocks as the world's best timekeepers. Pendulum clocks were used as time standards until World War II, although the French time service continued using them in their official time standard ensemble until 1954. Pendulum gravimeters were superseded by free-fall gravimeters in the 1950s, but pendulum instruments continued to be used into the 1970s.